In this video, we'll be looking at quantum numbers and the rules of filling electrons in orbitals. Quantum numbers. The set of numbers used to describe the position and energy of electron in an atom is called quantum numbers. Each orbital in an atom is specified by three quantum numbers: n, m, l, where n is the principal quantum number, m is magnetic quantum number, and l is the azimuthal quantum number. While each electron is specified by four quantum numbers, that is n, l, m, s. S is the spin quantum number. The principal quantum number n. It was proposed by Bohr, denoted by n. It determines the size of the atom by showing the distance between electron and the nucleus. It determines the energy of electron in an orbit. The maximum number of electrons in an orbit is given by 2n squared. No energy in an atom can have more than 30 electrons, where n is the energy level. It gives information about orbits, the K, L, M, N shell. Azimuthal quantum number. The azimuthal quantum number is also known as angular quantum number and is denoted by L. It was proposed by Sommerfeld. It determines the number of subshells to which electrons belong. It gives energy subshell. These are the energy subshell, the S, P, D, F, and this is the energy range. N and L is related by L equal to M minus 1. That is, for every L, we have M minus 1. Here L is the azimuthal quantum number and L is the principal quantum number. The maximum number of electrons in a subshell is given by 2 times 2n plus 1 in bracket. This is the summary of the azimuthal quantum number. Name of subshell: S, P, D, F. Value of L: for S we have 0, for P we have 1, for D we have 2, for F we have 3. Shape of subshell: S is spherical, P is dumbbell, D is double dumbbell, and F is complex. Maximum number of electrons: S is 2. Now, from our formula here, the value of L is 0 for S. So if you put 0 here, 2 times 0, that is 0. So 0 plus 1 is 1. 1 times 2 is 2. So maximum number of electrons is 2. For P, the value of L is 1. If you put 1 here, that is 2 times 1, 2 plus 1, 3. 3 times 2, 6. For D, the value of L is 2. So 2 times 2, 4 plus 1, 5. 5 times 2, that is 10. Maximum number of electrons in D is 10. For F, the value of L is 3. 2 times 3, 6 plus 1, 7. 7 times 2, 14. So maximum number of electrons in F subshell is 14. Magnetic quantum number. It is denoted by M. It was proposed by Zeeman. It gives the number of permitted orientation of subshells. The value of M ranges from -1 to +1. It tells about the splitting of spectral lines in magnetic field. M is related to L by M equal to 2L plus 1. That is, for every M, we have 2L plus 1, where M is the magnetic quantum number and L is the azimuthal quantum number. It gives degenerate orbitals. Degenerate orbitals are orbitals of the same energy. For P subshell, the degenerate orbital is PS, PY, and PZ. Spin quantum number. It shows the direction of electron and is denoted by S. -half and +half shows the spin rotation or direction of electron. It can be clockwise or anti-clockwise. This diagram below shows the direction of electron. This arrow facing up is the +half and the one facing down is the -half. So electrons are in opposite direction, each half. This is the summary of the quantum numbers and relationships. Let's go through this. N is principal quantum number, which is the shell. L is azimuthal quantum number, which is the subshell. Ym is the magnetic quantum number, showing the orbitals. For first energy level, that's n equal to 1, we only have one subshell, which is the s subshell, and it's 0, that is the azimuthal value. And this s subshell only has one orbital, and this name of the orbital is 1s. For the second energy level, we have two subshells, the s and the p. For the s has only one orbital. That is why we are having 0 here. For p has three orbitals, ps, py, and pz, ranging from -1, 0 to +1. And the name of this orbital for the s sublevel of the second energy level is 2s, while the p is 2p. For the third energy level, we have three sublevels, s, p, d. That is the azimuthal value, 0, 1, 2. For the s, as usual, s has one orbitals, p has three orbitals, ps, py, and pz, while d has 5 orbitals, ranging from -1, -2, 0, +1, and +2. The s orbital for the third energy level is called 3s. The p orbitals for the third energy level is called 3p, while the p orbitals is called 3d. For the fourth energy level, we have 4 sub-level or subshells, that is s, p, d, f. The azimuthal value is 0, 1, 2, and 3. For the 4s orbital, it only has one orbital. The p has 3 orbitals. That is why I have -1, 0 to +1. D has 5 orbitals. That is why it's ranging from -2, -1, 0, +1, and +2. While the D has 7 orbitals, ranging from -3 to +3. And the name of the orbitals for the 4 energy level is 4s, 4p, 4d, and 4f. Shapes of orbitals. The shape of s orbital. The s orbital has only one unidirectional orientation, and the shape is spherical. So this is the shape of the s orbital. Shape of p orbitals. The shape of p orbital is dumbbell, and it has directional properties, that is ps, py, and pz. Those are the orientation. And the shape for ps is in direction of s. This is the sy plane. The shape of ps in direction of s, same as py in direction of y, and pz in direction of z. Shapes of d orbitals. The shape of d orbital is double dumbbell, and it has a directional properties as well. So as you can see, it's double dumbbell, that you are having double. So this is the syz plane. syz plane. So this is the name of the orbital, dzs. For the second one, we have dsy. Third one, we have dyz. Fourth one, we have dz square. And the last orbital is ds square minus y square. So these are the 5 orbitals for the d subshells. Magnetic quantum number. It is denoted by m. It was proposed by Zeeman. It gives the number of permitted orientation of subshells. The value of m range from -1 to +1. It tells about the splitting of spectral lines in magnetic field. M is related to L by m equal to 2L plus 1. That is, for every m, we have 2L plus 1, where m is the magnetic quantum number and L is the azimuthal quantum number. It gives degenerate orbitals. Rules of filling electron in various orbitals. The first one we have is Pauli's exclusion principle. It states that no two electrons in the same atom can have the same value of all the 4 quantum numbers. That is, if an electron has n equal to 1, l equal to 0, m equal to 0, and s equal to plus half, no other electron in that same atom can have these 4 same value or identical value. So this is what the Pauli exclusion principle is saying. Aufbau's principle. Aufbau's principle states that electrons are added one by one to orbitals following increase in energy. That is, electrons are added from the lowest to highest. This is the energy level, and this is how electrons are added. 1s first because it has lower energy, then 2s because after 1s get 2s, that is the increase in energy, followed by 2p, followed by 3s, followed by 3p, followed by 4s, followed by 3d, followed by 4p, followed by 5s, followed by 4d, followed by 5p, followed by 4f, followed by 5d, and followed by 5f, then continue like that. This is the range for the energy of subshell energy: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and on. Hund's rule of maximum multiplicity. It deals with filling electrons on equal orbitals having same energy level, that is, degenerate orbitals. Hund's rule of maximum multiplicity states that electron is firstly singly filled before being paired in a degenerate orbital. This minimizes electron repulsion. That is, electrons are filled singly first before being paired in a degenerate orbital. So this is the way electron is filled, and this is the correct way. You want to have 3 electrons to fill in a degenerate orbital, you fill them singly first. So this is correct. And the second one, you have 4 electrons to fill. First of all, you fill singly to occupy all the orbitals. Then the last one, you start again from the beginning and start filling till it exhausted. This is correct as well. Then this last one is wrong. This is a wrong way of filling electron, and this is what the Hund's rule is saying, that first of all, you have to fill all these orbitals before being paired, but this was being paired first and it was not completely filled. So this is a wrong way of filling electrons. Let's solve problems on quantum number and electronic configuration. Number 1. How many electrons can be accommodated in subshell for which n equal to 3, l equal to 1? For l equal to 1, this is the p subshell. So the p subshell is in the 3rd energy level. So this will be 3p. P sublevel has 3 orientation, which we know, the ps, py, and pz. And these 3 suborbitals rather be taking 2 electrons each, so making total of 6 electrons. So our answer to this question is 6 electrons. Number 2, the number of 2p electrons having spin quantum number of -1/2 is, let's see, p subshell has 6 electrons, which we know, the ps, py, and pz, and each orbital contains 2 electrons, making total of 6. For s equal to -half, it means half of the electrons in the p subshell. So this will be what? 3 electrons. So half of 6 is 3. Which of the following quantum number for electron of an atom is possible? Let's see. For n equal to 1, l equal to 0, m equal to 0, s equal to plus half. Now we know that n equal to 1 means that this is the first energy level we are dealing with, and this first energy level has 1 sub level, which is the S, which is correct. And this sub level only has one orientation or one orbital, which is m equal to 0, which is correct. And it can take in 1 or 2 electrons, which is correct as well. So option A is correct. Let's see option B. N equal to 1. Yes, the first orbital. L equal to 1. That is the p sublevel. There is no p sublevel in first orbital. So considering this option B is wrong, that means option B is not possible. Let's see option C. N equal to 1, the first energy level. L equal to 1, the S sublevel. M equal to 1 orbital. Yeah, correct. S equal to minus half, that is 1 electron. N equal to 2, second energy level. L equal to 1, the p sublevel, which can be found in second energy level, which is called the 2p. M equal to minus half, which is correct. S equal to minus 1 over 2, which is not. So the option that is not possible here is option B. Number 4, write the electronic configuration of sodium. The atomic number of sodium is 11. So recall our energy range: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, and 5p. So let's write. We are filling in 11 electrons. So we have 1s2, 2s2, 2p6, and 3s1. This is the S. S can take in 2 electrons. The 2s can take in 2 electrons because it only has 1 orbital. The p has 3 orbitals, and each orbital takes in 2, that is 6. So you have 2 plus 2, 4 plus 6, 10. Then the S will take the last electron, which is called the valence electron, that is 1, making total of 11. Recall the atomic number equal to electron number because this is a neutral atom. So we are filling in 11 electrons. So we have successfully filled in the 11 electrons. So this is the electronic configuration for sodium. Total number of electrons here is 11. Write the electronic configuration for calcium. Now let's write, following our energy range: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So let's calculate. This is 2 plus 2 plus 6 plus 2 plus 6 plus 4, which is 20. The atomic number for calcium is 20. So, and it's equal to the number of electrons because this is a neutral atom as well. This is 2, 2, 4, 10, 12, 18, and 20. The valence electron here is the outer electron, which is 2. So valence electron for calcium is 2, and the valence electron that is used for bonding. Number 6, write the electronic configuration of this ion, Al3+. Atomic number is 13. Atomic number of aluminium is 13. So this aluminium is losing 3 electrons. That is why it's 3+. For a neutral aluminium, the atomic number is equal to number of electrons. But this has charge. That means it has lost 3 electrons. So the atomic number will not be equal to number of electrons. So for a neutral atom of aluminium, it's supposed to be 13. But now we'll be having 13 minus 3 that is losing. So the electron in this ion is 10. So we fill in 10 following our energy range. So recall our energy range. So let's fill 1s2, 2s2, 2p6, making 10. So we are safely filling 10 electrons. 2 plus 2 is 4 plus 6, that is 10. Number 7, write the electronic configuration for chlorine ion. Atomic number for chlorine is 17. This chlorine ion has gained 1 electron. So for a neutral chlorine, the electron is 17, but now it has gained 1, making 18. So we are filling in 18, following our energy range. So we have 1s2, 2s2, making 4, 2p6, making 10, 3s2, making 12, and 3p6, making 18. So we have successfully filled in 18. Number 8, write the electronic configuration for oxygen ion. Atomic number of oxygen is 8, and this oxygen has gained 2 electrons added to the 8 that it has. So we are filling in 10 for oxygen ion. So let's fill. 1s2, 2s2, 2p6, making 10. 2 plus 2 is 4 plus 6, that is 10. Electronic configuration of transition metals. The electronic configuration of transition metals is given as 1s, 2s, 2p, 3s, 3p, 3d, 4s. Not as the usual one: 1s, 2s, 2p, 3s, 3p, 4s, 3d. And the reason is for stability purpose. If you observe, the 3d comes before the 4s, and this particular chain is peculiar to the transition metals. The electronic configuration of transition metals can be written in noble gas form, that is argon 3d4s. If you observe very well, argon has 18 electrons, or the atomic number of argon is 18. So filling in the electrons, it ranges from 1s to 3p. So if you check our chain, from 1s to 3p, this represents argon. They have 3d and 4s. So that's why we write it as argon 3d 4s. Let's take example. Write the electronic configuration of the following: copper, iron, and chromium 2+. For copper, copper has atomic number of 29 and it's a neutral atom, meaning to have 29 electrons. So we fill in 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1, or in noble gas form, argon 3d10, 4s1. If you observe closely, after the 3p6, we have about 11 electrons left. So, and these 11 electrons can completely fill the D. So we fill in the D completely before the 4s. So this is 3d10. Then the last electron goes into s orbital, that is 4s1. For iron, the atomic number for iron is 26, and it's a neutral atom. That means to have 26 electrons. So we fill in 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2, or in noble gas form, argon 3d6, 4s2. Now, if you observe closely, after the 3p orbital, we have about 8 electrons left, and these 8 electrons cannot completely fill in the d orbital. Then we fill in the s orbital first before the remaining one now goes into the d orbital. That's why we are having 3d6, 4s2. For chromium 2+, the atomic number is equal to 24, and for neutral chromium, it will have 24 electrons. But this chromium is having 2+, that means it's losing 2 electrons. So for chromium ion, ion 2+, it will have 22 electrons. So we fill in 22 electrons. So this is 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2, or in noble gas form, argon 3d2, 4s2. Now if you observe closely, after the 3p6, we have about 4 electrons, and these 4 electrons cannot completely or halfly fill the 3d block. So that's why we fill in the 4s completely, and the remaining one goes into the 3d orbital. Thanks for watching. Please make sure you subscribe, and you can check my channel for other interesting videos. Thank you.